Hello, my name is Samantha Christie and I'm really pleased to be here today from the system planning team at the Australian Energy Market Operator. I'm going to be speaking about our national transmission planning approach on system strength. Firstly, about how we fit broadly into the planning and regulatory environment, and then about how we set minimum fault level requirements for system strength and how we project any shortfalls. Of course, planning for system strength in the NEM means planning for the power system transition, and system strength is one of the key technical attributes that we're making sure to focus on as the system changes. There are two major trends that we keep in mind when we are planning for system strength services and what might be needed in the future. The first is the fact that currently and traditionally, large synchronous generators have provided system strength in the system, but as they retire or as they begin to operate flexibly over the day and maybe between seasons, that's something we need to plan for. Second, we need to start planning for and continue planning for the introduction of more and more inverter-based resources into weaker areas of the system. With system strength, we are looking at the ability of the system to provide sufficient fault level or sufficient resilience to changes in the voltage waveform, and that traditionally has been provided by injection of fault current from synchronous generators, but there are a range of different ways that we're looking at planning for that system strength and resilience as the system changes. A lot of our thinking is captured in some documents that are already published. So for example, if you're keen to see what AEMO is thinking for a system strength outlook in the NEM, we have the 2020 Integrated System Plan published earlier this year with an appendix number 7, Power System Security, which specifically looks at system strength outlook in the NEM over the next couple of decades. Of course, the Renewable Integration Study considers trends and opportunities and requirements as increasing numbers of renewable generation connect to the NEM, and system strength is touched on in that Stage 1 report from the Renewable Integration Study. We will be releasing a dedicated system strength report later this year. We expect it to be published in December. It is the first in an annual requirement that is now included in the rules to look at the requirements and shortfalls for system strength. We have a system strength requirements methodology on our website which explains how we currently design and plan and project for system strength. And of course, system strength is touched on in our power system requirements reference paper. Our current regulatory arrangements require that AEMO set fault level nodes across the NEM and then calculate minimum fault level amounts required at each of those nodes as a kind of proxy for system strength provision. We will publish a report every year. It used to be ad hoc, but it will now be done every year, noting those requirements and including projections for system strength amounts and any shortfalls that we see coming in the next 5 years. Those reports also touch on whether or not, where there is a shortfall, us declaring a requirement for the local transmission network or jurisdictional planning body to go and make available services or to procure services in some way to deliver those system strength services. One thing to note is that these requirements are for the system as a whole, and newly connecting generators, my apologies, must remediate their own impact as they join the network. Now to how we set the fault level nodes and the minimum requirements. First of all, we take a look across the network and we see where would be a good point to measure how system strength is going. We have decided that as AEMO, we think it's appropriate to look at a variety of different points with different properties when we're looking at system strength. We choose to create for each region in the NEM at least one fault level node which is at a metropolitan load centre, one which represents kind of the centre of synchronous generation, which is contributing to fault levels. And also as levels change at this area, we consider them to be an early warning of system strength issues in the region. We choose one which has, at least one, which has a high penetration level of inverter-based resources, and also one that represents areas where the section of the network is electrically remote from synchronous generation. And of course, in each region, we can decide on more than one node for each of these categories, but we broadly use these categories to give a good scan of system strength requirements across a region. Here I am showing on the map the spread of different generation types across the Queensland network to give a sense for the fact that, for example, in central Queensland, there's a centre of synchronous generation, which has certain system strength requirements and properties. In the north, there are some synchronous generators right up at the north, which are contributing to system strength. And then in between, we're seeing increasing penetration of inverter-based resources, and that's something we need to plan for from a system strength point of view. We previously had a system strength node down at Nebo, and we decided to move the node up to Ross earlier in 2020 so that we could be focusing more clearly on where system strength issues are emerging. This chart shows the importance, in our view, of planning for how synchronous generators are connecting to and dispatching in the NEM. You can see here that since August 2018, we had certain numbers of synchronous units online in central Queensland typically. This is their typical online bidding and dispatch pattern in the NEM. And you can see that towards the middle of 2020, we had fewer units available, and consequent system strength constraints being brought in Queensland to manage the impact of that change. This slide is just designed to show the importance of us anticipating or understanding where different units will be performing and dispatching in the NEM. Taking that understanding of the nodes and projections for minimum synchronous machine combinations, we calculate the three-phase fault level at each of the nodes that we've selected. And if we're concerned that there is a shortfall approaching, we also do detailed electromagnetic transient analysis using PSCAD in order to understand the full detail of the fault level requirements at that level. I've also listed down the right-hand side of the slide the success criteria that we use when we're deciding whether or not a minimum fault level amount at a node is sufficient and we can consider it to be a steady state that we can plan to. So here we see the minimum fault levels that were decided using this process for Queensland. And I do note that right now we are reviewing these levels because we will be releasing a 2020 system strength report later this year. And so some of these may change, but this gives an indication of the fault level requirements across Queensland, which reflect our understanding of system strength requirements. So once we have set those minimum requirements across a region, we turn to project how system strength will look over the coming years and see whether or not there are any shortfalls that need to be addressed. We use fault level as a proxy for system strength, and we look at the 5-year outlook. We take what is our best expectation at a particular time for dispatch of synchronous machines, and we often choose to take that from our integrated system plan projections, although sometimes we update them with the latest information, for example, from the modelling from the electricity statement of opportunities. And then we do an assessment to consider whether we see a shortfall between the projected amount of fault level contribution from plant that we consider will be online and dispatching, and the minimum fault level that was already calculated for each of the nodes in the previous stage. Here you can see a representation that will often appear in some of our reports, our system strength reports anyway, showing the expected amount of time that we think that the fault level will be above the minimum requirement shown there in the dotted line across a year. And we project this for each of the 5 years in the 5-year outlook and look to see if there are situations, as you can see there in this Ross chart, where for a sufficient portion of time, we expect that we will not have enough fault level in order to declare a shortfall. Where you can see the lines there dipping below the minimum requirement, sufficiently worrying there for us to declare a shortfall. And we did in fact declare a shortfall at the Ross node in northern Queensland in April 2020, and PowerLink is currently looking at how best to address that shortfall. Of course, PowerLink will have a range of options available to it to address the shortfall. I've listed here some of the options that we've seen in the past, so the use of synchronous condensers, synchronous generators in synchronous condenser mode, installation of transmission network equipment. However, because this is an emerging area of study, there are also other options such as tuning of inverters, run-back schemes, grid-forming inverters, which are emerging, and we expect this to be an area of strong technological innovation in the next couple of years as the industry as a whole adjusts to the new system strength situation. As we move forward with our planning for system strength in the NEM, these are some of the considerations we're keeping in mind. That system strength and inertia today are provided incidentally, and that the provision of those services in future will be closely linked to the timing of any power station closures, reduction in minimum demand projections, and our expectation for how best we will be integrating new inverter-based resources across the NEM. The 2020 Integrated System Plan gives some indication of our thinking on this. And of course, we know that the Australian Energy Market Commission is continuing to review these frameworks to make sure that they're fit for purpose. And they're currently considering rule changes to these frameworks to make them better serve the needs of the system in the future. We think that system strength remediation will become increasingly common over the next few years, both for the regional requirements and for newly connecting generators. And we do see a role for the industry as a whole to consider strategic investments and how they can play an important role in realising efficient outcomes. Thank you for your time.
Today I'm going to be talking about the Electranet Main Grid System Strength project. This is a regulated network project seeking to resolve system strength and synchronous inertia gaps declared for the SA system. On the left you can see a map of the South Australian transmission system. South Australia is connected to the NEM via two interconnectors. The Hayward double circuit AC interconnector in the southeast and the Murray-Link DC interconnector in the Riverland. The Adelaide Metropolitan Load Centre is also the location of all large baseload synchronous generation in the system. There's significant inverter-based resources connected to South Australia. 2,500 megawatt capacity is currently either installed or committed. Majority of this is wind generation, but there is also 3 grid-scale solar farms and 3 BESSs connected. As you can see on the map, there's significant concentration of this IBR within the mid-north of the state. Demand in South Australia is predominantly fed in the metropolitan Adelaide area, but there's also significant mining load in the upper north of the state. The Metropolitan Load Centre is also home to significant distributed energy resources, 1,400 megawatts of capacity connected to all of South Australia, the majority of this located within Adelaide. The past 10 years have seen substantial change in the supply-demand behaviour on the SA grid. On the screen we have 3 different sets of duration curves. SA grid demand supplied, SA inverter-based resources dispatched, and SA synchronous generation dispatched. If we look first at the SA grid demand supplied, we can see that peak summer demand has not changed materially in the past 10 years. South Australia typically supplies a peak summer demand of about 3,000 megawatts each year. If we look next at the minimum demand supplied, we can see that it has been falling over time, and in particular has accelerated in recent years. South Australia now sees a record minimum demand supplied each springtime for daylight hours. Looking more generally at the curves, we can see that the energy under these curves has been falling steadily over time. The changes in grid demand patterns are attributed primarily to the uptake of distributed energy resources within the state. If we look next at the inverter-based resource dispatch, we can see the steady increase in share these resources have made of the energy supplied over time. Looking next at synchronous generation dispatch, we can see that the peak demand for synchronous generation has not materially changed. However, the energy under the curve for synchronous generation has changed substantially. Increasing commitment of inverter-based resources and uptake of DER has placed downward pressure on market pricing throughout the year, resulting in reduced synchronous dispatch over time. Minimum levels of system strength are required to ensure that the system can be operated in a secure and stable fashion. With the ongoing reduction in operational dispatch of synchronous generation for South Australia, AEMO was required to commence directions of synchronous generators to ensure minimum acceptable levels could be maintained. The graph on this page shows directions for South Australian generation in the last 5 years. It can be seen that between 2017 and 2018, a substantial increase in directions were required to ensure acceptable minimum levels of synchronous generation dispatch could be maintained. It is important to note that these directions are for system strength and not to ensure supply-demand balance is achieved. You can also see on this slide that in 2020, additional security directions were made during the outage of the Hayward interconnector following a fault within the Victorian transmission system. In addition to the system strength directions to ensure minimum synchronous generation dispatch is maintained, AEMO also maintains a system strength constraint that is used to ensure the maximum instantaneous dispatch of inverter-based resources within South Australia does not exceed the secure level for the current dispatch of synchronous generation. In response to the ongoing need to direct synchronous generation to maintain acceptable minimum unit commitment within South Australia, AEMO declared a system strength shortfall for the state under the NER fault level rule. The NER fault level rule uses short circuit levels as a proxy for system strength. AEMO is required to publish for each NEM region minimum acceptable fault levels at key nodes, and the local system strength service provider is then required to ensure that these minimum levels can be maintained. If it becomes not possible to maintain these minimum short circuit levels, then a system strength shortfall will be declared. In addition to declaring the system strength shortfall for South Australia, AEMO also declared an inertia shortfall, including a minimum requirement for synchronous inertia to be maintained within the state at all times. As a TNSP for South Australia, Electranet is the system strength service provider as well as the inertia service provider for the state. Following the declaration of shortfalls for both of these requirements, Electranet was required to examine and propose resolutions to the shortfalls. Electranet performed both economic and technical assessments in addressing the declared shortfalls. A key preference was placed on well-established and reliable technical options in addressing the gap, and therefore various combinations of synchronous condensers were examined as the network solution. With the declaration of the inertia shortfall, flywheels were also included on the synchronous condensers. The economic assessment compared the ongoing cost of AEMO directions against the cost of Electranet commercially contracting with generators to provide the system strength services required, and comparing this against the installation of synchronous condensers by Electranet as a network augmentation. The addition of synchronous condensers, including flywheels, was found to be the most efficient and least cost option compared to either directions or contracting of generation by Electranet. The declared shortfall listed minimum short circuit levels within South Australia as the requirement to be achieved. However, these short circuit levels are only a proxy for system strength, and therefore extensive EMTP studies were undertaken to verify that the proposed solution met the technical requirements. Following extensive studies, AEMO endorsed the technical solution proposed by Electranet. Electranet's proposed solution was to install synchronous condensers at each of the Davenport and Robertstown substations in the Mid-North region of South Australia. These sites were chosen in particular because of the close proximity to inverter-based resources within the area and the effectiveness of installing synchronous condensers at these sites as shown in the system studies. Tendering was undertaken and delivery of two 129 MVA synchronous condensers with flywheels was awarded to GE for Davenport. Subsequently, further tendering was performed for the Robertstown site, and Siemens was awarded the contract to deliver two synchronous condensers with flywheels at the Robertstown site. All four synchronous condensers will have flywheels providing inertia of 1100 megawatt seconds per synchronous condenser, or a total of 4400 megawatt seconds of system inertia, which meets the minimum inertia shortfall declared by AEMO. In addition to resolving the system strength shortfall and meeting the synchronous inertia requirements declared by AEMO, installing synchronous condensers at the Davenport and Robertstown substations results in improved voltage control in the Mid-North region of the state, easing of SA system strength related constraints on existing inverter-based resources, and the easing of voltage stability constraints associated with prior outage conditions in the Mid-North region. Construction at both sites is underway, with Devonport commencing first and Robertstown following afterwards. Electronet is currently working with AEMO to finalise the integration of the synchronous condensers into system limits and operating instructions. Commissioning at Devonport is scheduled to commence in the next month, while Robertstown is scheduled to follow in 2021. The installation of synchronous condensers resolves the system strength and synchronous inertia gaps declared by AEMO. However, the SA grid requires more than strength and synchronous inertia in order to operate securely, particularly when at risk of islanding from the NEM. To enable sufficient frequency control, generation ramping capability and supply and demand balancing is necessary, and sufficient levels must be provided both for intact and islanded conditions. AEMO has declared residual inertial requirements related to fast frequency response capability, and Electronet is working with AEMO to resolve these new requirements. Thank you.
Hello everyone, welcome to my second presentation of the day. In this presentation, I will be sharing some of our experiences with system strength issues that we have had in Queensland and how we have managed to improve the system strength using existing assets such as SVCs and inverter-based renewable resources without actually increasing the fault level. This presentation highlights the fact that system strength is not just the fault level and how rightly tuned IBRs can actually supply the system strength than consuming it. This is a map of Queensland transmission network showing synchronous plants, existing IBRs and SVCs. Some interesting facts about Queensland transmission network that make Queensland network very special not only in Australian context but on a global scale. Australia has developed world's longest and thinnest grid, stretching about 5,000 kilometers, and Queensland transmission network is the longest in NEM, spanning over 1,700 kilometers. In September 2020, 59% of the total Queensland load was supplied by renewable energy sources. About 680 megawatt of rooftop PV was installed in 2019-20 alone, which is very close to the biggest baseload generator in NEM, that is of 750 megawatt. North Queensland, without any baseload power plant, currently hosts about 1100 megawatts of large-scale IBR plants and at times supply almost 100% of its load from renewable energy sources. For some of the IBRs in North Queensland, the closest baseload synchronous plant is about 1,000 kilometers away. North Queensland and Central Queensland are very rich in terms of number of SVCs connected. There are total 17 SVCs in North and Central Queensland region. So, in terms of system strength challenges, what we have is high penetration of inverter-based resources. We are very rich in SVC and STATCOMs, and those IBRs are far from synchronous sources and large variation in load. And this basically makes a condition as all the stars are aligning for perfect system strength challenge. And it really makes a perfect condition for a weak grid. One of the main issues that we have seen in Queensland due to low system strength, and that is not really any different from rest of the NEM, is the control interactions. What it means that all those inverter-based plant, they interact with each other and cause some sort of instabilities. And when we look at this diagram, the number of SVCs and the IBRs in one area, it's no surprise why we see the control interactions. And as we add more and more plant, system inherently becomes weaker and the possibilities of control interactions increases. So what we have done in Queensland, we have used our SVCs and existing renewable plant to minimize those control interactions, or in other words, I can say to increase the system strength without actually adding fault level to the system. So in first example, I'll be talking about SVC tuning. So as you can see, there are two existing SVCs, one in Townsville area and one in Warri region. So what we saw in North Queensland, as more and more IBRs were connected, system became weaker, and we started to observe some control interactions. These two SVCs, because of their control structure, provided some flexibility to modify their control system, and we worked closely with the manufacturer of those SVCs and designed a different control system that basically reduced the control interactions and increased the hosting capacity of that region by a few hundred megawatt without actually adding any fault level or, in other words, synchronous support. What I'm showing you here is the system response with old settings of the SVCs, and we can clearly see here that once fault was removed, there were some sustained oscillations in the voltage, and clearly showing some level of control interactions. And what I'm showing you here, you can at about 16 seconds after the fault, at 16 seconds, we basically triggered the new settings or the new control of the SVC, and we can see that oscillations are damping down, and we clearly see response improving. And at around 20 seconds, we switched back to the old settings, and we can see as soon as we switched to the old settings, those oscillations increase again, and hence showing that having the right control system in place can minimize the control interactions. Now, this is the second example of where we improved system strength by retuning some of the existing plants, and in this case, it's existing renewable plants. In this particular case, what we identified that one particular plant was the main contributor to the control interactions. However, it did not provide much flexibility in terms of retuning or improving the control system of this particular plant. But what we identified that in that region there were other plants that did have some flexibility in terms of their control system and the settings, and we worked very closely with the manufacturer of those plants and simulated the case with the different control system. And what we observed that when those new settings and new control system was in place, clearly we saw improvement in those control interactions, and control interactions were minimized. So what I'm showing you here is the system performance without retuning of those IBRs. And what we can see after fault clearance, we can see oscillations in the voltage, and showing that there are some control interactions. And when new control system of those IBRs put in place, we can see it helps minimizing those control interactions, and we can't really see any oscillations in the voltage. So the key is, again, here we could have got the same response by increasing the fault level of the area. In other words, we could resolve this problem by adding more fault level in that area. However, the point that I want to highlight here is if we tune the control system correctly, we can also improve the system strength. And the key to this success of control retuning is the partnership with the OEM, because our experience is without this partnership with the OEM, these retuning are not possible. In terms of the learnings that we have had from retuning of the control systems, is that synchronous condensers are not the only option for system strength remediation. The root cause of the system strength issues could be with the deficiencies in the control systems that is in place. So it is very important to understand the root cause of the system strength problem, as issues could be resolved by barely retuning of the control system. And what I have shown you here is that IBRs are not always a problem in terms of system strength. If control system is rightly tuned, IBRs can in fact supply the system strength than consuming it. And this brings my presentation to end. Thank you.
Good afternoon. My name is Stephen Sproul from Hitachi ABB Power Grids. Today I will discuss grid-forming converters. Grid-forming converters are not a new technology, but applying them on interconnected power systems to resolve issues such as system strength is a new application. So quickly providing some context. Synchronous generation is being displaced or retiring. On the left, we can see the planned coal generation fleet retirements, and on the right, challenges with low system strength, which is being covered extensively today. As we source more of our energy from renewables, unless we can provide system strength through another means, we will always have to maintain a minimum level of synchronous machines online. So what services do we require to operate a stable and secure grid? Well, as you can see, we need inertia, system strength, voltage control, and frequency control. Synchronous machines provide all of these services, and whilst we have several options in terms of technology to provide voltage control and frequency control, we can only get system strength from synchronous generators, synchronous condensers, and grid-forming energy storage. Now, whilst traditional grid-following energy storage can provide voltage control and very fast frequency control in the form of fast frequency response, or FFR, only grid-forming energy storage can provide inertia and system strength. So we'll now discuss converter technology. Here we have three types of converters. On the left, we have grid-following converters or current source converters. Nearly every PV and energy storage system connected to the NEM today is a grid-following converter. Grid-following converters have a mechanism called a phase lock loop, which we can see at the bottom left. These devices lock onto the grid waveform and follow the grid, hence the name grid following. These devices try and push current onto the network to provide energy as a service. The challenge with these converters is if the grid waveform is compromised, there can be challenges with instability in these converters because they have challenges following the grid during post-fault conditions or other such contingency events. When we move to the middle converter, this is a grid-forming converter or voltage source converter. These converters provide a voltage and frequency and have typically been used in an off-grid context. They provide a voltage and frequency reference to establish an off-grid network and hence are called grid-forming converters. The challenge with grid-forming converters is that they do not operate well in parallel with other voltage sources, whether that's synchronous generation or the grid, and can have a very stiff response in terms of operation in these scenarios. This brings us to the right, virtual synchronous machines. Virtual synchronous machines are grid-forming converters plus the dynamic behavior of a synchronous machine. The comprehensiveness and detail of virtual synchronous machines vary from vendor and have different levels of complexity. Here is an example of a 5-part virtual synchronous machine model, which contains a virtual impedance, inertia model, governor model, AVR model, and rotor flux model. As the picture shows at the bottom, this acts like a shock absorber. It allows the grid-forming converter to operate in parallel with other voltage sources, if they are synchronous machines, or the grid. Without this critical layer, you do not get the dynamic behavior from a grid-forming inverter that is conducive to operating on a network. It allows the voltage, frequency, dynamics, sharing, and inertia to be tunable. So the key factors of grid forming and virtual synchronous machines are they do not have phase lock loops. They cannot be compromised if the grid condition is affected. They are independent voltage sources. They do not rely on the grid to provide their voltage. And as such, they can operate at very low short circuit ratios. Depending on your definition, they can operate down to a short circuit ratio of 1, or otherwise being the only source in the network. So to characterize the behavior of grid-forming converters or virtual synchronous machines, we will look at a real-world example. Here we will look at a sequence where a grid-forming energy storage system is operating in parallel with the NEM, and at point 1, the 132 incoming line protection opens, and then at point 3, the local substation protection opens, forming an independent island with the grid-forming converter and local loads. Here we see the current and voltage waveforms from the sequence just described. On the left, we see the voltage waveform at the 33 kV bus, and on the right, we see the current waveform output from the grid-forming converter. On the left, we can see throughout the sequence, the voltage waveform remains constant. There is no notching, interruption, or distortion. And then on the right, we can see initially to point A, there is just a small current contribution, and this is in fact the voltage source converter syncing the harmonics on the NEM before the 132 kV incoming line opens. We can see that the grid-forming converter's current response is immediate because it is now the only voltage source in the grid, so the current supplied is load dependent. And then after about 70 milliseconds, the local substation protection opens and the current provided is just the local load requirements of the now independent grid. Throughout this sequence, the converter is always in grid forming operation, and the reason it is able to do this both in parallel with the NEM and islanded is because of the critical virtual synchronous machine layer. This layer allows the grid forming converter to operate in parallel with the grid. Again, you can see because the converter is providing a voltage sinusoidal waveform on the left, the current is a consequence of the scenarios that occur and hence give it a very fast response when you look at the time step on the x-axis and the speed of response of the current waveform. This brings us to the key technical services grid forming converters can provide that grid following converters can't, and that's virtual inertia and system strength. This slide describes how grid-forming converters can provide virtual inertia and is an important concept to understand in the context of system strength and how grid-forming converters do not rely on measurement. In the top left, we have the power transfer equation, which dictates the real power transfer from the converter to the grid. We have the product of the voltages of the grid and the converter divided by a coupling impedance and the sine of the phase angle between the two voltages, the grid and the converter. This is the exact same equation that dictates the inertial response from a synchronous machine, as we see on the right. So when we look at the phases on the left, we can look at the far left, and the grid and the virtual synchronous machine are both spinning at 50 Hz. Now remember, a grid-forming converter has its own voltage and frequency reference, so it has its internal speed spinning at 50 Hz. If we then go to the phasor on the far right, we have a negative rate of change of frequency event, where the grid slows down and the grid-forming converter remains at 50 Hz. So in this case, the grid actually moves away from the virtual synchronous machine that remains spinning at 50 Hz and creates this phase angle. This is how you get an inherent real power response from a virtual synchronous machine without the need to measure. It is not looking at what the grid frequency is doing and responding. The grid moves away from the virtual synchronous machine and the power contribution is a consequence. Now, depending on how the virtual inertia coefficient is set, will not dictate the initial response, but it will define how fast or slow the red phasor catches up with the grid. So in summary, not all converters operate in the same way. It's important not to broadly categorize all power electronics as having the same challenges. Grid-forming converters were developed for the off-grid market, but now offer on-grid benefits. Grid-following converters, PV and energy storage, are affected by stability issues on weak networks. Virtual synchronous machines are just grid-forming converters plus the dynamic behavior of a synchronous generator. You cannot get inertia or system strength from a current source or grid-following converter, and replacing or allowing synchronous machines to switch off is the key problem grid-forming converters or virtual synchronous machines solve.
Good afternoon. My name is Stephen Hinchliffe of GST Advisory, and I'm pleased to present on managing system strength during the transition to renewables. In undertaking the study, we modelled, using PSS SynCal, the system strength on the North Queensland transmission network under normal and worst case N-1 contingency and under different scenarios of renewable energy penetration. We chose a size of synchronous condenser of 400 MVA as being a typical size that you might place in a centralised location to provide cover, system strength cover that is, over a broad area. We looked at 1 times 400 MVA in key locations, and then 2 times 200 MVA in key locations to overcome N-1 issues, and 4 times 100 MVA again to overcome N-1 issues where you might have a number of outages in the network. And then finally we modelled 8 times 50 MVA distributed in renewable energy zones in a similar manner to what would happen if the proponents of renewable energy schemes were required to install their own synchronous condensers. We also undertook an economic life cycle assessment of the capital and operating costs to determine economies of scale of synchronous condensers. The diagrams here show the impact of putting a single 400 MVA synchronous condenser at Murrumbidgee in North Queensland. The green dots show very high system strength provision flowing through the yellow, orange and then red, and then white is no benefit. And as you can see, there's on the 400 kV network and some of the subtransmission network, there's good system strength provision. The diagram on the right shows what happens under worst case N-1 contingency, and you can see there that a single 400 MVA unit really doesn't provide system strength over a significant part of the network. And in that case, a better approach will be to provide multiple, say up to 4 medium-sized units to overcome those N-1 contingencies. We approached a number of manufacturers of synchronous condensers to obtain budget prices for different sizes of unit and for multiple units. and used our internal network connection costs database to determine typical prices for connection of different sizes of synchronous condensers. We also drew on manufacturing data to determine operating costs, not least electrical cost for the excitation of the condensers. As the plot shows here, there's a significant economy of scale arising from selecting larger units than, for example, installing multiple smaller units. This is all based in a total of 400 MVA of provision, either 8 times 50 MVA units through to ultimately 400 MVA units. There's roughly a 40% to 50% increase in life cycle costs going for multiple larger units as opposed to single units or a select few strategically placed medium-sized units. This slide presents a summary of our findings from the study. We looked at different network topologies and then determined the optimal approach to system strength provision. For low impedance, good N-1 contingency, that is well-meshed network, such as the 275 kV backbone throughout most of Queensland, the optimal approach is to install large centralized synchronous condensers strategically placed. For low impedance but poor N-1 contingency, that is not well-meshed networks, 2 or more medium-sized units strategically placed provides the optimum solution. And finally, for high impedance, low voltage networks, distributed multiple small units associated with renewable developments represents the most economic approach to providing system strength. In September of last year, I was fortunate enough to be invited to one of ERCOT's network planning and stakeholder consultation sessions, and then subsequently to meet with some of their senior network planning engineers. We talked about some of the similarities between Australia and particularly states like Queensland with high penetration renewables in the west of the state remote from load centres. They pointed me in the direction of one of their reports, Dynamic Stability Assessment of High Penetration Renewables, for which there is a link on this slide. Unlike in Australia, UK and New Zealand, Texas does not have an economic regulator. Rather, it is ERCOT's responsibility to ensure loads and generators are connected in a technically competent manner, and that the integrity of the network and hence electricity supply is maintained. This is what the Texans use to call the Panhandle. It's a map of Texas. And as you can see, there's a significant amount of renewable generation in the west, whereas the load centres tend to be in the east and south. ERCOT undertook a study of a scenario with maximum power transfer from north and west Texas to load centres around the I-35 corridor. The study case conditions highlighted the reliability changes associated with the potential future operation scenarios characterised by low inertia, low system strength and high penetration renewable generation. Key findings were inverter-based generation controllers require significant system strength for reliable operation. This is one of the plots that they showed me, which is roughly a 6 Hz modulation on the mains voltage arising from a network disturbance that triggers a syncopatic operation between inverters. As I mentioned earlier in my slide, because the inverters operate in an uncontrolled manner to a system disturbance in that one tries to correct the disturbance, the other then overcompensates and so on, there tends to be a roughly 6 Hz modulation on the voltage waveform which is undamped, and as you can see here, gradually increases in amplitude until it reaches the extremes of the voltage limits on the network. A number of speakers have already talked about the system strength related constraints placed on VRE connected to the Redcliffe to Horsham to Ballarat line in northwest Victoria. The main point I would like to make with regard to this is that the issue was resolved in part through improvements in the inverter software control systems and settings. And indeed, one of the recommendations of our report is that the better approach to resolving the system strength issue is not to continue with the palliative response to system strength by installing synchronous condensers, but to address the root cause and work with inverter manufacturers to improve their control systems such that inverters don't detract from system strength, but perhaps can support it. A number of inverter manufacturers have recognized the issue with control systems on traditional inverters for solar PV and wind turbine generators, and have developed what Siemens calls a synchronous generator emulating inverter, or SGE. It aims to emulate a synchronous machine by using the same steady-state droop and dynamic characteristics. The excitation mode is used to provide reactive power and voltage amplitude. Whilst it does not respond instantaneously to a network disturbance, it does respond sufficiently fast to react before network and wind turbine generator stroke solar farm over voltage protection is triggered. Siemens and ABB and many other inverter manufacturers are now looking to improve the development of inverters to be able to provide system strength, and indeed this ABB and Siemens inverter is able to provide up to 3 per U overcurrent in response to a network disturbance. Thank you for your interest in my presentation. I'm pleased to take questions, you're welcome to contact me directly at stephen.hinchliffe@ghd.com. Thank you.
As I start, I'd like to thank Amo and Seagray for this opportunity to share AGL's views on the ongoing system strength issues. As one of the largest generator retailers in the Australian electricity market. As a brief introduction, AGL's Grid-Scale Technologies business unit looks after grid connections delivery, including GPS and connection modeling studies, plant commissioning and R2 testing across large-scale and distributed assets, including C&I customers. We also look at emerging technologies ranging from next-generation inverters, energy storage such as pumped hydro, thermal, and hydrogen, and assesses opportunities to demonstrate, introduce, and scale the deployment of these newer technologies into the mainstream energy market. AGL has a highly diverse asset technology portfolio, spanning both large-scale transmission-connected assets, both green and black, as well as distribution-connected or behind-the-meter technologies, such as embedded PV, batteries, and virtual power plants. Our existing large-scale generation fleet spans thermally fired synchronous plant to the latest inverter-based wind, PV, and batteries, which provides a portfolio mix challenge, as existing aging synchronous plants are gradually being retired and replaced by inverter-based variable renewable generation. However, the current generation on inverter technology does not provide the fuller range of dynamic grid support services such as fault level, short circuit capability, and also synchronous inertia necessary for voltage and frequency control, which then leads to the ongoing challenge of maintaining supply reliability and security, in particular system strength, even as renewable energy uptake accelerates in the NEM. Given the bespoke nature of system strength issues, as the earlier speakers have described, a diversity of solution options working in combination, that is, a Swiss Army knife type approach, stands as the best likelihood from a whole of system and market perspective to collectively arrive at a technically and economically efficient solution, leveraging on the relative technical and commercial strengths of each solution. For example, there would be a role for sources of system strength from synchronous machines, with flexible, fast start synchronous generation providing both system security as well as reliability services to the grid. Now, one trade-off in offering fast start capability, particularly in gas-fired aeroderivative and reciprocating engine-based plants, is the typically lower inertia of these plants in the range of 1 to 2 seconds, which can impact certain aspects of the fault right-through performance characteristics of such plants. Synchronous condensers or syncons provides a tried and trusted solution that has been well demonstrated in other jurisdictions such as in Europe to support higher levels of renewable energy integration and represents a socialized, regulated network solution approach to ensure diversity of system strength solutions. Of course, we should note that Syncons does not provide megawatts and therefore does not address supply reliability requirements. As for inverter-based or IBR generation, newer technologies that can provide system strength as well as other dynamic grid voltage and frequency support such as grid forming, voltage source converter, short circuit current and fault level contribution will be desirable in order to backfill the retirement of legacy synchronous plant. Also, appropriate plant control system settings that can enable regional network plants to operate in a stable manner, in particular to minimize incidences of inverter control system interaction or SSCI under a reasonably diverse range of system operating conditions is also another key desirable. This approach, of course, was demonstrated in the recent successful resolution of the Western Murray constraint, which also affected, among others, inverter generation plant such as AGL's Broken Hill Solar Farm and Silverton Wind Farm. Now, as for DERs, in particular, distributed PV and virtual power plants does have a supporting contribution to the overall network system strength issue by ensuring that embedded generation has sufficient capability to ride through voltage faults and to not exacerbate primary dynamic stability issues on the transmission network. This points to the need for flexible dynamic DER technical standards, in particular those relating to medium voltage and low voltage network voltage management and dynamic fault ride-through network support. Lastly, new network infrastructure is part of the overall Swiss Army knife, in particular to reduce network electrical impedance and also to provide N-1 coverage of any planned or unplanned outage of critical transmission assets. Going forward, a range of considerations spanning technical, regulatory compliance, and commercial aspects presents both challenges and opportunities in this area, both within Australia and internationally. Firstly, definition of system strength issues and new market services, including interpretation and application of the do no harm principle in new generator connections that is broad enough given the locationally specific and technically bespoke nature of system strength issues, but also providing sufficient direction and incentive to allow the market to specify and deliver technically and commercially efficient and co-optimized solutions. Secondly, the challenge of arriving at the right technology mix in replacing aging thermosynchronous generation, in particular balancing flexibility, availability, reliability, and security, and also the commercial and economic risks and all uncertainties presented by a rapidly evolving and variable NEM generation mix. The third challenge is to achieve an optimal mix between network and non-network solutions, in particular control tuning-based solutions, amidst the backdrop of an increasingly power electronic and software-defined power system. This would involve a solid technical understanding of the underlying physical root cause mechanisms of the adverse voltage instability or interactions, so that a reasonably optimal decision between, for example, a Syncon-based solution versus retuning of affected plant control settings. The retuning should also include dynamic network support plant, such as SVCs, as a relatively low-cost and quick-to-deploy short to medium-term solution, whilst longer-term or permanent solutions, such as new synchronous plant and new transmission infrastructure, are being planned. The next point pertains to fit-for-purpose power system modeling. In particular, the availability of wide-area EMT models or modeling study capability to the market so that new generation proponents have the visibility of potential system strength issues earlier in the project development process. This includes the ability to undertake connection studies that provides basic considerations of system strength or weak grid related issues. Point number 5 relates to possibilities around incentivizing innovation to market, in particular, developing new system strength solutions. Valuable innovative attributes include flexible and responsive firming generation, grid-forming inverters with new capabilities such as overload and short circuit capability, and also new improved plant control strategies. This of course should be accompanied by mechanisms to support proof of concept demonstration and uptake of these new solutions, such as the role played by ARENA and the Clean Energy Financing Corporation. Lastly, Australia is not alone in tackling system strength issues, and our NEM community can leverage off global expertise, lessons learned, and proof of concept for new technologies from international jurisdictions. In closing, solution flexibility and diversity, coupled with appropriately balanced mix of regulated network and market-driven incentives, are important enablers for technically effective and commercially sustainable mitigation for system strength issues. Such solution diversity would also assist in meeting the overall supply quality, reliability, and security objective, consistent with the Australian National Electricity Objective, and ultimately serve the interests of electricity consumers. Thank you for your attention.